The purpose of this video is going to be to introduce some of the concepts that you learned in chemistry last year, so we can put them in the context of biology. So it's going to be really important that as you watch this video you take really good notes so that we're able to kind of hit the ground running, right? So if you look, right, so everything is made up of matter, right? And so matter is made up of atoms, and we're going to kind of put this in the context of, what are things that are useful for us in biology, right? And so, if I have a hydrogen atom, it's made up of a proton, and it's also made up of an electron. Okay, and oxygen, right, is made up of protons, neutrons, and electrons, and it has a different number, right? And so, right, like we see that this collection of atoms, right, is contained kind of within the periodic table, and we're going to really be concerned with just a certain number of these, right? So we're mostly concerned with the ones that I've kind of put, right, a red box around. So hydrogen, sodium, magnesium, potassium, calcium, carbon, nitrogen, oxygen, phosphorus, and sulfur, right? So a couple of things that are really important is that there are 25 elements that are really essential for life, and 4 of those elements make up 96% of living matter, and those 4 elements are carbon, hydrogen, oxygen, and nitrogen. Right, so those 4 elements really comprise 96% of the living matter, but there are 4 elements that make up most of the remaining 4%, which are phosphorus, sulfur, calcium, and potassium. That's not to say, right, there really are 25 elements that are really essential for life, and one of those elements, right, a good example here, right, exists when you have an iodine deficiency. Right, and so right, when you have an iodine deficiency, you can often end up with a goiter, right? It's called a goiter. So there are often these trace elements in addition to these kind of 4 major ones, plus these other 4 elements that make up the majority of that other 4%, that are also necessary in small quantities in our bodies, right? So with atoms, right, an atom is the smallest unit of matter that retains the properties of an element, right? So I have an oxygen atom. Right, so I have an oxygen atom, I have a carbon atom, a hydrogen atom, and a nitrogen atom. Those are our big 4, right? And so we have those 3 subatomic particles that make them up. We have protons, which are positive, right? We have neutrons, which are neutral or have no charge, and we have electrons, which carry a negative charge. Okay, and so if I was to look, right, at something on the periodic table, right, if I was to go back here for a second, right, and we take a look. Right, and if we just flip back really quick, you're going to end up, right, and so having, so let's take maybe say a look at like lithium, right? So if I looked at lithium on the periodic table, right, so I'm going to have lithium, and then I'm going to see a 3 above it, and then 7 point something below it, right? So the number above it, right, this is the atomic number, okay, and the atomic number is the number of protons. And then this number below is the mass number. And the mass number is really the number of protons plus neutrons, right? And then there's obviously like a fraction of that, which is electrons, because electrons have a very small mass, okay? We also can end up with isotopes, right? And isotopes are the same element, right, with a different mass. Right, and that happens. So for example, an example of that might be carbon, right? So with carbon there are a couple of common isotopes, and they all have a different mass because, right, you have a different number of neutrons. So you're always going to end up, right, like for it to be the same element or same atom, right, it has to have the same number of protons, but the number of neutrons can vary, and as the number of neutrons varies, that gives us an isotope. Okay, so that's what atoms are going to look like, right? And then what we're really concerned with is like Okay, so how do atoms bond and how do they join together to form molecules, right? And so here, if you look here, right, this is, right, you can very clearly see it's got how many electrons, right? So what we're representing outside the nucleus is the number of electrons. So as you can see, it has 2, 8 more, it has 10, it has 18, right? So this has 18 electrons. And so the electrons are really what's going to determine its bonding, right? So electrons are going to determine how it bonds. Okay, and that depends upon the number of electrons that are really in what we are in the valence shell, right? So the valence shell are the ones on the outermost shell. Currently, right, this one has 8 valence electrons, right, because there are 8 electrons in the outermost shell, and since that's the case, right, that's going to affect how it bonds, right? Since this has 8 valence electrons, it's a very stable atom, right? It actually doesn't want to bond with anything else, right? Because the purpose of bonding is really to like become more stable, right? Your goal is to fill your valence shell. And since this already has a full valence shell, right? This, if you look at the next one, right, is argon, right? This is really argon. And since it has a full valence shell, right, it's stable. Okay. So if we look here, right, you can see. So here's right the section of the periodic table that we're kind of a little bit most concerned with. Okay, and so if you look, right, so as you go across, right, we call these rows. As you go down, we call these groups. Okay, and so again, your behavior depends upon your valence shell, right? How the atom is going to behave. And atoms, right, in a group exhibit the same chemical behavior, right? Because if you notice, right, they have the same number of valence electrons, right? So if I was to go across, this is really group 1, group 2, okay? And then, right, you're going to see that we're going to have the break in the middle, right? And so 3, 4, 5, 6, 7, and 8. Okay, so those group numbers are really related to the valence electrons, right? And since the atoms in the same group have the same number of valence electrons, they behave kind of in the same way, right? And so the atoms in this group, right, which are the noble gases, right, are inert, meaning that they're stable and they don't need to react, right, because they already have a full valence shell, right? Because if you notice, right, these have a full valence shell. Because if you remember back to chemistry, right, the first shell holds 2 electrons. The second shell, right, which you can see here, is going to hold 8 electrons. And the third shell is going to hold 8 electrons. Okay, and again, your goal is to fill that valence shell. So then, how do you fill that valence shell if you already don't have 8 valence electrons? Well, you're going to do that through bonding, right? And so there's 2 major types of bonding that we're going to talk about. One of them is covalent bonding, right? And so with covalent bonding, you're going to share electrons, okay? And how you share electrons is all based on electronegativity. Right? So for example, oxygen is more electronegative than hydrogen, right? Meaning that it wants electrons more. Right? And it wants electrons more because it's more electronegative. Okay, and then, right, so we're going to get into, right, so like for instance here, if you see this, right, this is methane, CH4, and these share it, they have equal electron affinity, right, so they share electrons equally, right, and since they're going to share electrons equally, this is going to form a nonpolar molecule, right, so when they're sharing equally, we're going to form a nonpolar molecule as we share. Okay, as for instance water, right, it's going to share electrons unequally, right, because oxygen wants these electrons just a little bit more than hydrogen's, right, because it has a higher electron affinity because it's more electronegative. Okay, and we're going to talk a little bit more about water specifically because water is going to be a really key kind of piece to biology. So a second type of bond that we often see is an ionic bond, right? Now, an ionic bond, right, is not where you're going to share electrons now, right, but where you're going to exchange electrons. Right, so that means somebody's going to give up an electron, and then another, right, atom is going to get an electron. Okay, so for instance, you can see here sodium, right? Sodium, if it gives up one electron, is going to become stable, right? Because it will have a filled valence shell. And if it gives it up to chlorine, now chlorine has 8, right? And so now chlorine has a filled stable valence shell, right? So as I become positively charged, right? If you remember, we're called a cation, and as I become negatively charged, I'm an anion, right? And then you get an ionic bond, right? Because this positive and negative charges will attract each other, right? So as these charges attract each other, you get an ionic bond. So let's look at water a little bit more specifically, right? So with water, oxygen is going to be more electronegative, right? And hydrogen is going to be less electronegative. Okay, and so that means that the so while oxygen and hydrogen, right, since this is a covalent bond, right, they're going to share electrons, but they're not going to share them equally, right? So this is what we're going to call a polar covalent bond. Okay, and a polar covalent bond is where we're going to get unequal sharing of electrons. Right? So they're going to spend a little bit more time with the oxygen than they are with the hydrogen, right? So that's why this means partially negative and this means partially positive, right? So the oxygen is partially negative and the hydrogen is partially positive within water as we have this polar covalent bond. Well, since that happens, right, we also end up with hydrogen bonds, right? So hydrogen bonds are very weak bonds. And that exists, right, because we have this attraction, right, between that partially positive hydrogen, right, and then what's going to actually be this partially negative nitrogen, right? So as we get this hydrogen that's partially positive, we're going to get that attraction between that partially negative nitrogen, and we get this weak hydrogen bond. Okay, so that's kind of one example, right? And so then this right, like, is not a covalent bond, right? Like, they're not sharing. It's this weak attraction between these molecules. Okay, so you hopefully have walked away, right, from this video kind of spiraling back to what you learned in chemistry in terms of like elements, atoms, right? And then we want to put this in kind of a biological context because we're really going to focus on water, okay, as we move forward this week, and we want to make sure that you understand the difference between ionic, covalent, and especially polar covalent bonds and hydrogen bonds as well.